Welcome everyone. So we are starting our last session and the first talk from Paul Wiegmann, University of Chicago, and he'll be talking about semi-classical limit of the Beth Ansatz equation and finite gap solution of soliton equations. Here you are.
Okay. Well, thank you very much. Mary, my apology for listening the same talk again. I talked on the same subject half a year ago in Hangzhou on your conference. That is the same subject. And this subject is based on the subject of the talk. The talk is based on joint work with Valdemar Melin, Yuta Siguchi, and Konstantin Zaremba. Okay, the story is the following. We spent considerable time at least people of my generation spent considerable time of their life in study quantum integrable systems, and that basically means solvable either through factorized theory of scattering or through Beth Ansatz, depending on the nature of the problem. But at the same time, there is an adjacent subject of solving classical systems, classical integrable system. It's basically the same system. One is classical, another is quantum, and we get to almost perfection of solving quantum system. We understand a lot of things, but some other people also get perfection of solving classical soliton equation and also know about a number of things. But unfortunately, for many, many years, as far as I remember myself being introduced to the subject, relation between these two is remain a mystery and not well developed as well as each of these subjects separately, taken separately. Indeed, there are books, many books on soliton equations, classical. There are many things about quantum integrable systems, but there is a gap in between them. These books are sitting on different shelves and basically overlap is, if exists, is very minimal. So the story which I'm going to say, to talk about is some hint that a certain progress could be made. It has not been made, in my opinion, up to now, but there is some chance that it could be, those two subjects could be connected. There's no surprise about it because semi-classical limit is a singular limit, and even in quantum mechanics it's a tricky singular limit. Semi-classics is complicated. And so the story which I'm going to say is about semi-classical limit of the Beth Ansatz and its relation to finite gap solution of soliton equation. So I would, the problem which I focus is a case study, sort of, one particular equation, which is a modified KdV equation, well known. Its solution is well known. There are soliton solutions, there are periodic solutions. A periodic solution could be periodic or multi-periodic, and the simplest periodic solution is called Snoidal wave. Snoidal starts from Sn, and it's elliptic sign. And this is one of the oldest solutions, like colloidal waves, found probably Korteweg by himself. But at least it goes back to time of Korteweg. The sinusoidal wave is simply elliptic sine and characterized by elliptic moduli k, and k determines the period of this function. It's a periodic function, so k is arbitrary parameter, period is arbitrary parameter, and delta naught is also arbitrary parameter for this equation. That is one of the simplest and historically one of the first solution of periodic solution of soliton equations. Of course, there is solitons, but the limit of this sign. So the question now is, what if I quantize this equation and solve it? Once it's integrable, it should be solvable somehow, even in quantum way. Can I get this sinusoidal way or something like that? And how to get it from the Beth Ansatz equation, from methods which we use for solving quantum integrable equations. Okay, that's a subject. Let me repeat that this MKTV chosen for a specific reason, but this is just a case study. Probably the same method which I would like to describe could be applied to some class of other familiar equations, but we focus on the sinusoidal wave. Okay, so what is Beth Ansatz? It's equations which quantize momentum of particles, many particles in the system, actually infinitely many. Each they scattered by phase phi, which depends on the momentum, and n is integer. And this is how momentum is quantized. Once we know how momentum is quantized, we can choose a state, quantum state, state of interest, computes the energy. Once we know momentum, we can compute the energy, and perhaps can do large limit of large number of particles, such as it will be not simply collection of particles, but a continuum medium. Then we can compare it with periodic solution of, for example, some soliton equations. Okay. Let me spend half of my, I plan to spend half of my time by sort of physical introduction of two classical equations and then comment about Beth Ansatz. Okay. So MKDV equation has definitely Lax representation, and in this case, Lax operator of modified KDV equation is simply Dirac operator. Lax operator for KDV equation is a Schrödinger operator, and here is Dirac operator. So what does it mean? It means that if delta is a solution of MKDV, it is a periodic function. Then this doublet psi plus and psi minus are Becker-Hazer functions. Epsilon is the spectrum. We can find the spectrum from this equation. It's well known. It could be found by algebra geometric method. It's one of the simplest example of algebra geometric method developed by Dubrovin, Novikov, Krichyar, Matveyev, Itz, and many others. And for that particular solution, the spectrum of Dirac equation, epsilon, it's on the vertical axis, and on the horizontal axis is momentum. This is how the spectrum of Dirac operator behaves in the presence of periodic solution, sinusoidal wave. So the spectrum consists of three bands. This is the first, they're symmetric. Obviously, spectrum is symmetric with respect to zero, energy equals zero. So there is a lower band, then there is a central band, and again lower band, so you can see the symmetry. And those are allowed bands, accessible bands. So if you give me momentum, for example, this number, then I can find the energy. Okay. Between them, there are gaps, two gaps, as you can see, which means that if you give me energy inside forbidden gap, I will not be able to find solution of Dirac equation in L2. I can find equation, but this equation will not be normalizable. So it's forbidden band. Okay. Normally, as we all know, ordinary partial differential ordinary differential equations in periodic potential have bands and gaps, and normally number of bands and gaps is infinite. It's also well known that if periodic potential is solution of soliton equation, then the number of gaps and consequently bands is finite. And this is called finite gap solution. So basically, if you ask me, find me delta, it's a periodic function such that the spectrum will have finite bands, then we know that this function will be periodic static periodic solution of some solitonic equations. Right? And the simplest one is number of gaps is minimum, and this is the case here, because spectrum is symmetric, number of gaps should be 2. That's a minimal possible solution, and solution is sinusoidal wave. Okay. By the way, I will appreciate questions in the middle of the talk. So I try to keep it simple. Okay, anyway, so if you give me periodic solution of mkdv, I will plug it here, and I find the spectrum as a function of p. This is how a spectrum is. And that's, of course, this picture is a real projection, real cross-section of a Riemann surface. In this case, this Riemann surface is a torus. This Riemann surface is actually Schottky double. That means that there is a real cross-section, and when energy and momentum are real. So that's this graph is. Okay. One of the major applications, one of the interesting and very kind of suggestive, instructive application of sinusoidal wave of mkdv equation in this setting is so-called Peierls phenomena. Let me briefly say what it means. Consider one-dimensional crystal. One-dimensional crystal, it's a position of ions, it's black dots sitting on a line. Those dots those ions could vibrate and fluctuate a little bit about the equilibrium periodic positions. Okay, now let's place electrons to the system, and they, of course, will interact with ions, and ions provide periodic potential for electrons. But this potential is kind of dynamical, because ions can move it themselves, and they decided to find the best position to make electrons happy, energetically happier. What Peierls phenomena is that says that if number of electrons, it's a red dots here, is exactly equal to the number of sites, it's called half-filled band, then apparently electron will ask ions to be displaced from the equilibrium position as it's drawn on this picture. It's called Peierls distortion. So ions move a little, this ion move a little bit to the right, this ion move a little bit to the left, such that their position will be double periodic. And if we, it's a sort of remarkable phenomenon and very counterintuitive. So electrons do not like periodic potential, electrons like double periodic potential. And if you draw displacement of ions, how much this ion displaced from its equilibrium position, we'll get a periodic wave. And it's happened that this is a sinusoidal wave. Okay. Peierls basically proved this theorem saying that electrons, in order to minimize their energy, will force ion displaced in a periodic manner, and the period will depend on how many electrons are in the system. First, he exposed this phenomenon in 1930s, but didn't publish it until 1954. And it says that one-dimensional equally spaced chain with one electron per ion is unstable. So they form this double periodic lattice. That gave a subject to a big subject in condensed matter physics, which is called electronic crystals. So crystals, electrons apparently want to organize environment where they not form a gas but a crystal. Okay, if you look for how this energy express itself in terms of the spectrum, here is what happened. So consider spectrum of non-relativistic electrons. It is on this page, on this graph, where right, and then black dots are ions, and then electrons force ions, to be displaced a little bit in a periodic manner, in such way that the spectrum now open a gap on the chemical potential. That's one gap. Okay. In 1964, in 60s, this phenomenon has been proved experimentally, and that's a standard graph from Wikipedia, I guess, where you can see this periodicity in one dimension. These lines are periodic structure of electrons. They sort of visualized, and this is by Werner Little. Okay, Wikipedia also displays a very kind of pleasant picture of Peierls himself with Pauli and Dirac in Cambridge. Okay, but only in mid-80s, mostly with the help of Igor Kricheyer, Peierls phenomena has been associated with finite gap solution of soliton equations. So one can formulate it in the following way. Consider, for example, consider a difference equation for psi, and n is the position on a one-dimensional lattice with some coefficients, variable coefficients Cn, right? It's a difference equation. And then you compute the spectrum of this operator. the spectrum will depend on, of course, on C, and ask, find Cn, it's a number associated, it's a discrete set of numbers, such that the energy of the system, namely sum of the spectrum from the very bottom up to number of electrons, how many electrons you put in up to chemical potential, find sum and find the best C which minimize these electrons. It's sort of fundamental problem, and Igor Krichever with his co-workers Natalia Kirova and Sergei Brazovsky prove, and Zeloshinsky prove a theorem in mid-80s that the best C are finite gap solution of soliton equations. It's not obvious at all, but this is a sort of well-established, almost mathematical fact. Okay. And the theorem is here. The extrema of the energy is given by the finite gap solution of the Toda chain. The system is discrete, so it's a chain. Okay. Yes. Okay, while proving this fact, Krichever and his co-workers identify the Schrödinger equation for those electrons in the presence of ions with the Lux operator of Toda. Okay, and in continuum case, it will be Dirac, Lux operator is Dirac operator, and instead of Toda lattice, we will have a modified KTV. Okay, so the problem is to consider Dirac Hamiltonian. I wrote it here. It's it depends on the gap on the mass term, and this mass term allowed to fluctuate. Let's find it such that it minimizes the energy, and that will be a solution of KTV, of MKTV. Okay. Okay. So once we know the period of this sinusoidal wave K, we can compute the number of particles in the system, or the period is given by elliptic integral. Okay. And here's a full set of solution. The spectrum given by a spectral curve, which corresponds to a torus. That's density of states, the differential of momentum related to differential of energy. It's called density of states. And the gap edge spectrum has edges, 1, 2, 3, 4 edges, and these edges are given by elliptic modulus of elliptic integrals, which depends on how many particles you put in the system. That's basically solution. So now the question is, can we obtain that interesting formula from the textbook, well established, even experimentally verified, from the Beth Ansatz? Suppose the system is, after all, equations, electrons are quantum. Okay. Well, we can consider this equation, this problem as a quantum, not semiclassical. We don't minimize the energy, we simply allow the system fluctuates, delta fluctuates, and study how Fermi's electrons live in this sinusoidal wave. Okay. And that's not a problem, because this problem is equivalent to what is called Grosny-View problem. So if you want to integrate over delta, it will be psi4 interaction, and that's known problem of quantum field theory in one dimension, which is called Grosny-View model, and it's known to be integrable. The problem, however, is that it doesn't have semiclassical parameter. However, if one introduce flavors and say that number of electrons have a color or flavor, and there are flavor runs from 1 to n, generalize this model, introducing those flavors, then a semiclassical parameter appears, and semiclassical parameter in this case will be large M. So the strategy, what we did is we solve this Gross-Neveu model with arbitrary n, send n to infinity, and expected to obtain this Noidal wave with all these elliptic functions, and that indeed happened. So I spent the remaining of my time, which is 4 minutes, but allow me 5 minutes to briefly glance on the solution. So the problem is, again, I take a Gross-Neveu model. It's a standard model, again, case study in quantum field theory. This model has a symmetry, which is a Lie group, orthogonal group with even number, with even rank to n. I would like to solve it by the Beth Ansatz, and this solution is known, solved also in mid-80s. Take the solution, send n to infinity, and see whether you get periodic solution of MKDV equation. Okay. A few words about quantum integrable models with Lie group symmetries. Also in mid-80s, so those models have been solved for arbitrarily simple Lie group. And I also participated in this development together with Eugene Agiyevsky and Nikolai Reshetikhin. And the story is basically the following. So once you know, once you have a Dynkin scheme, Dynkin scheme is the Dynkin diagram plus automorphisms of Lie algebra, and in this case it is orthogonal group, algebra of orthogonal group, which is Dn series. Then this data, which encoded in Dynkin scheme, sufficient to write and therefore solved the Beth Ansatz. In particular, this problem developed a complicated spectrum with many particles, and number of particles corresponds to each fundamental representation of this group. Among them, there are 2 spinors with given masses and other antisymmetric tensor and the vector multiplet of defining representations. So the masses in this case, but it's also for a arbitrary Lie group. Lie algebra, simple Lie algebra are known. They are written in this box. Okay. Also, the S matrix is known. Solution of Yang-Baxter equation is known. Solution and S matrix which obey unitarity and cross-unitarity also has been found in quite general form. Once you have this S matrix, one can write the Beth Ansatz equations. And case phases which particles accumulate, it's a certain matrix element of the S matrix, and if there are many particles, discrete Beth Ansatz equation becomes integrable equations, and those are 2 written here. Okay. Once you solve this equation for certain states, you're able to compute momentum and energy, and the relation between them is the spectrum which known for the Noidal wave. Okay. So opening literature in mid-80s, we find this phases. So phases are written here for spinors scattered by other spinors. Spinors have different chirality. Spinors scattered by vector particles or antisymmetric tensor. And then how antisymmetric tensor scattered by itself. This box contains a full set of the data necessary to proceed. Right. There is not much specific here. It's simply unitarized solution of Yang-Baxter equation with O2n symmetry. Okay. One may consider a particular. Yeah, I know my time is up. I need another 1 minute. So one may consider different states, and the states which you have to guess which states, there are many states in the quantum system, which states would correspond to this nodal way. And it has been guessed and then checked that it is a state where vacuum equally filled by spinors with positive right-hand chirality and left-hand chirality. This is how they scattered, and eventually their momentum or rapidities occupied an interval from some number to another number, symmetric interval, and once we solve this equation with a given k, we'll obtain solution which depends on the edges of this interval, and computing the momentum, number of states we identified with number of particles in the system, and they determine the edges of it. So that's a standard strategy. The only problem is, and this is a standard strategy for Beth Ansatz, it can be done, although those kernels are pretty complicated, but we are not interested in that. What we are interested in, what happened if n is going to be large. And if n is going to be, right, so to simplify the matter, in this box I wrote how these kernels or faces which particle accumulate, basically it's a unitarized solution of Yang-Baxter equations read. That is those is kernel written in Fourier space. In Fourier space, they a little bit looks a little bit more compact than in coordinates in the momentum space, but this is how they look. Okay, so now we send n to infinity. This number which stays here, it's only place where n is present, 2n minus 1, 2n minus 2. Those who know, remember representation theory of Lie algebras from high school, recognize it with the Coxeter number, dual Coxeter number. This is 2n minus 2 for series D. So this number we would like to send to infinity. As soon as we send it to infinity, you will see that the kernels, this faces becomes singular. It's sort of a Bose condensation here. N to infinity, this exponent becomes equal to 1, collide with this 1, and so it's a kind of singular limit. So if n to infinity sent to infinity, we obtain singular kernels. And the problem then will be reduced to these two simple equations, which has, it's an integral equation with a singular column kernels, which are in a sense equivalent to Riemann-Hilbert's problem. If n is finite, it's rather complicated and hardly solvable integral equations. If n goes to infinity, they become equivalent to the Riemann-Hilbert problem, which could be solved in an elementary manner, and solution remarkably so shows the spectrum of the cnoidal wave with all the details. It was quite interesting to see. how classical results about of Kerdevegis himself obtained 150 years old, almost 150 years old ago, with after some hard work in fighting with Beth Ansatz, appears out of this mess and complexity of the Beth Ansatz, and it's indeed happened. Okay, so the message which I would like to deliver, and this is my last slide, is that once the quantum system has a clear semiclassical parameter, and in that case, this is a large rank of the Lie group, then semiclassical limit could be achieved, and comparison with the soliton equation term by term could be also achieved. Thank you very much, and I stop now.
Yes.
Pavel, the electron gas wants to distort the lattice in order to minimize the total energy. But the distortion of the lattice also costs the energy. Is that included in your Hamiltonian? I did not understand that fully. So
yes. Yes. I understand. Yeah, I understand the question. Just a moment. Let me put it down. Right. So here is a Hamiltonian. And Andreas, you see the Hamiltonian, do you?
Yeah, right.
Okay. The first part, this part, which consists of fermions, that's fermionic energy. And this part is a cost of distortion. So ions don't want to be in periodic positions. They don't want to be disturbed. If you disturb them, they cost energy. And this is elastic energy which we have to pay. So there is a competition between, one second. Just one second, if I find the proper page. Yes, there is a competition between energy of electrons, which wants ions to be displaced, and the energy of ions, it's this term, which wants ion, and then ions don't like to be displaced. So they compete. And it's absolutely remarkable, and this is Parel's observation of 1930s, that electrons win in one dimension. In higher dimension, it's dubious. Sometimes they win, sometimes they don't. It's model dependent. But in one dimension, electrons are driven by Pauli principle, are so powerful that they make ions, bosons, to be slaved of these electrons. So it's a competition. A difference between them is pure numerical number. And I remember this number from being student. It's 2 divided by pi. Apparently it's less than 1. And this is how they compete. So electrons produce pi, ions produce 2, and 2 is less than pi.
And that is better than Pavel's solution, right? So the you discussed is better than the distortion that Pavel's found, right? I mean,
yes. Electrons are stronger, but it's absolutely not obvious, and it's a competition between 2 and pi.
Yeah.
Ratio between the two terms is 2 divided by pi. So it's not obvious, but apparently it's always happened. And it's universal and almost model independent. It's model dependent.
Maybe time is up.
Yes, the time is up.
Thank you.
Okay, thank you very much. Let's thank Pavel again.
Thank you.